I'd like to thank the organizers for inviting me here, and let me discuss today the Meissner effect. This is a long title indeed, and the details of the work I'm going to talk about were published earlier this year in here. The work is done in collaboration with Nick Grohl and Rinel Ceaurescu at Florida State University. Okay, here is an outline of my talk. First, I'd like to discuss what the Meissner effect is and what's so nonlinear about it. And the impurities will play a very important role here. And what we try to understand is that to what extent the dirtiness of the surface in niobium cavities can result in what I'm going to talk about. We know that the surface of niobium cavities is far from perfect, that there are impurities there. And what I'm going to show is that that can change a lot of the way the Meissner effect occurs in cavities. Then I'll describe a nice technique used at Florida State. It's a thin film strip resonator, which allows us actually to measure the Meissner effect comparatively easy by measuring the frequency shift due to the magnetic field applied parallel to the film. That can be described using this theory based on Usadel equations. The agreement is very good. And what we can see is that indeed the Meissner effect in dirty films is nonlinear. And that can play a significant role in cavities. Okay. So let me first describe you the textbook features of the Meissner effect. If we apply the parallel magnetic field to the surface, the magnetic field is screened and decreases exponentially with the distance from the surface. So we know how the field is screened here. We can calculate the current density, and it's simply the magnetic field divided by the London penetration depth. Now, if we have 100 millitesla, and we calculate the current density, what we get is a very high number. It's 10 to the 8 amps per square centimeter. And this is about 5 orders of magnitude higher than any depinning current in niobium. In niobium, pinning is very weak. So the typical JC in niobium is 10 to the 3, 10 to the 4 amps per square centimeter. So we have 4 orders of magnitude difference. So even if we apply only 1 millitesla to the surface, Meissner current will be 3, 4, 5 orders of magnitude higher than the pinning current. So pinning is so weak compared to the Meissner currents that we can neglect it. So, so all this can be obtained from the model developed by Fritz London. That's his picture in the 30s. And basically, what he said was very simple. We have superconducting state, so we can divide electrons into the normal electrons and superconducting electrons. And the density of superconducting electrons decreases and vanishes at Tc. So the sum of the two equals the total electron density. This is, of course, a very simple model, and in many ways it's an incorrect model, but it captures the main features of superconductivity. And then what we can do, we can simply apply the Newton law to the superconducting electrons. This is the second Newton law. The critical current density time derivative is simply equals the driving force. So this is accelerated motion. And that is very different from the Ohm law, which is the viscous motion. Now, if we take this and substitute it into the Maxwell equations, that gives us the London equation, which describes screening of the magnetic field with the London penetration depth. So this is a so-called linear Meissner effect. So everything is linear here. Screening is described by the linear equation. We can describe it more formally by writing the superconducting current, which is proportional to the vector potential. And this is a London penetration depth, which depends on the mass and the carrier density. So we should have the electron density, superfluid density here. And so everything is linear until the superfluid density starts depending on current. And that happens when the current, when the field is strong enough. So current densities are not small. And as a result, NS here depends on current density. So the relation between A and J becomes nonlinear. And that's what I'm calling nonlinear Meissner effect. And that indeed happens. And that certainly happens in superconducting cavities, because in the best cavities we can apply currents flowing on the surface of superconducting cavities is close to the pairing limit. And there are several tricks here. Trick number one is that the answer depends strongly on impurities. If a superconductor is clean, then the nonlinear Meissner effect is absent at low temperatures. And this is a very non-trivial feature of that, simply because at low temperatures, Ns equals the total electron density, so it doesn't change, no matter how fast my condensate moves. However, in the dirty case, when we have non-magnetic impurities, Ns is not equal to the electron density, and then it depends on current, and that's what I'm going to talk about. Actually, that was understood in the 60s by Bardeen and others, and what they showed was that in the clean limit, the superconducting gap as a function of current stays constant, and then it drops to 0 as we reach the pairing current density at low temperatures. And that is very different from the conventional Ginzburg-Landau theory tells us near TC. Near TC, there's a pair breaking effect. Superconducting gap decreases to this point, and that drops to 0. So the case of 0 temperature is very different from the case of the temperature close to TC. In the dirty limit, the Ginzburg-Landau result remains the same, of course, but the low temperature gap actually is affected by current density, even at 0 temperature. And so there is a pair breaking effect. So we can actually measure it, and that's how people do it. If we have nonlinear dependence of current density on the vector potential, this is a linear part, and this is nonlinear correction. The first nonlinear correction in the vector potential is quadratic. So, okay, we have J, which depends on A, like this. So if we apply periodic AC field, this is a magnetic field, then what we have the so-called intermodulation. So the periodic field generates higher order harmonics, simply because we have nonlinear dependence of J and A. And the next harmonic will be the third harmonics. And people actually can measure it, and that's how they can tell that Meissner effect is linear or nonlinear. And there's a theory developed about 10, 15 years ago, and that was used to measure nonlinear Meissner effect in different superconducting materials. The problem with understanding of these results is that we apply the AC field, so we drive superconductor in and out equilibrium, because now it's nonlinear. So it's very hard to say if what we're measuring really is nonlinear Meissner effect or it's a feature of non-equilibrium state. We can understand it slightly differently by introducing the surface impedance, which contains surface resistance and imaginary part. And the imaginary part of the surface impedance is nothing but what people usually call kinetic inductance. And kinetic inductance is simply the kinetic energy of superconducting currents, because they're frictionless, they move in and out, and they have inertia. We can calculate the kinetic energy of superconducting electrons by introducing the kinetic induction. That will be the kinetic energy. And on the other hand, we can write the kinetic energy like simply the kinetic energy of superconducting electrons, the mass, the density, the velocity. This is a volume. And use the expression for the superfluid velocity in terms of the vector potential. And what we get in the end is this formula for the kinetic inductance. The kinetic inductance is simply proportional to the squared of the London penetration depth. Now, if we have nonlinear Meissner effect, this quantity, this London penetration depth, will depend on the current density, simply because London penetration depth depends on superfluid density, and superfluid density is affected by current. Then we can simply measure the frequency of the resonator strip line, which will depend on the kinetic inductance. And if we apply strong field, it will be frequency shift. And that frequency shift can be measured, and that's what we did. So here's the geometry. The geometry looks like this. So this is a thin film niobium, pattern like this. So here is a strip line, about 3 millimeters long. And RF comes in here and comes out there. Here are the parameters. It's about 65 nanometer thick niobium film. This is 3 millimeters. This is 100 microns across. And the resonant frequency is about 20 gigahertz. This is a half wavelength mode. And what we can also do, we can put 3 sets of coils here, and we can apply DC magnetic field in all 3 directions. So what we want to do is to apply the magnetic field parallel to the film. And then we can rotate the field in this plane and see what happens. And because we don't know exactly where 0 is, because there's always a misalignment, we have 3 coils, and we can find a position where we know that we're exactly in a Meissner state. And this is very important here in the film geometry. So we have a resonator frequency, which is inversely proportional to the total inductance, and this is the capacitance of the strip line. Now, if my inductance changes a little bit, that gives me the frequency shift. That'll be the kinetic inductance at 0 current, at 0 field, minus kinetic inductance at the given field. And this is a total inductance which we can measure. So by measuring this as a function of magnetic field applied parallel to the film, we can measure the nonlinear Meissner effect. So then why would magnetic field affect the signal? Well, it's very simple, because if we apply magnetic field parallel to the strip line, the DC magnetic field induces current loops like this and like that, if we have the field inclined by the angle phi with respect to the axis of the strip. And if we have a nonlinear dependence of the current on the vector potential, now my vector potential contains the sum of the RF field and the DC field. So they couple together. If they couple together, I have the Y component of the vector potential flowing this way. This is induced only by the DC field. And the X component in this direction contains the sum of the DC field and the RF field. And now you see that only this component is coupled with the RF field, and there's angular dependence. So if we plug everything together, we can calculate the total current density. Sorry, the total current, RF, linear in the very weak RF field, which we use to probe that. And that lambda will depend on the magnetic field because of the nonlinear Meissner effect, because of that term here. So what we can see here, this is a correction, which is quadratic in DC field. It depends on the thickness of the film, and it also has an angular dependence. So we can test all these features, the quadratic dependence on the magnetic field and the angular dependence, and see how it works.